come from earth science stream, and one of the major requirement in earth science is earth science is all about field work, collecting data, applying new techniques, borrowing techniques from other disciplines like medical science, taking tomography, X-ray tomography, or back projection from physics. So it's all about data collection and field studies. But somehow in last few decades, we were actually lagging in data collection. There was people were not keen in taking up new observations. Especially in my discipline, it's all about setting up stations, setting up observatories in the field, collecting data about earth sciences, collecting data about physics of earth, collecting data about earthquakes. So somehow we sort of, India, or in fact Indian subcontinent, it lagged behind in data collection. And that has led to, it has got serious implications. I mean, we certainly lag in understanding several processes, several physical processes which operate over Indian subcontinent, especially the earthquake occurrence processes. But I must tell you, especially the youngsters, I also consider myself young still, is that it's fun. Data collection is a lot of fun. Setting up observatories in places like, this is Barren Island, which is the only volcano we have in India, on Indian subcontinent. This is somewhere in Andaman. This is beautiful place. This is Yamunotri. So it takes you, the fieldwork takes you to all Char Dham, in Himalayas. This is an old monument in Rajasthan. This is somewhere in Ladakh again. This is Antarctica. So GPS, the geophysical fieldwork is a lot of fun. So we need to gear up. We need to collect more data to bridge this gap what we have with other countries. And what I'll do in this, for my work, I use basically the GPS, which is there in your mobile phone. It gives you coordinate, but I deal with very high accuracy coordinate. I deal with sometimes fraction of a millimeter level accuracy GPS coordinate. So what I do is I take my GPS, I install them, and I keep estimating these coordinates on daily basis, or sometimes on second basis, or even millisecond basis, and then see its variation, how these coordinates are varying, and then try to understand, then try to correlate them with plate motion or the earthquake occurrence process, the deformation which occurs during the earthquake. So I'll give you just two examples here in this presentation, one from Himalayan region and one from Indo-Burmese arc. If I don't get time, then I'll skip the Indo-Burmese arc part. So so it's all about data collection, setting up observatories and then collecting the data. And you need to collect them in large numbers. That's one of the key in earth sciences. In fact, that's becoming true with all disciplines, that you need to have good data and large amount of data. Because if you have just one or two data, you can use a simple technique, or you can use a simple mathematical analytical formula, and then you can fit your curve into it. But if you have large amount of data, that requires new technique, that requires a more detailed explanation and detailed analysis. So you need to collect more data, and that's the key in earth sciences. So before I go into further in my talk, so my talk is basically on plate motion, understanding the plate motion, how this plate motion it causes earthquakes, and what are the deformation signature of earthquake cycle, which are the regions where we expect earthquakes to occur, and what are we doing about those regions. But before I start, what I'll do is I'll give you 3-4 slides so that my task becomes easier. So using GPS, so we have this Earth, which is where we have several plates. We have 8 major plates on the Earth, which are moving with respect to each other. And GPS is a tool which has given us a very reliable technique to estimate these plate rates. So like for example, this is Indian plate, and there is a GPS at IISc Bangalore, which tells you that the Indian plate is moving at a rate of about 5 centimeter per year. So 5 centimeter per year is like is almost like growth of your nail. So it's 52 millimeter in 50 weeks or something. So it's almost like 1 millimeter per week. So all of us, we are enjoying this ride at a rate of 1 millimeter per week, which nobody bothers. But actually, so that's the 1 millimeter per week rate by which we are all moving. And as I said, nobody bothers, but we are bothered about it, because it's this motion which causes earthquakes in the Himalayan region. It's just very tiny motion of 1 millimeter per year, which causes earthquakes here, earthquakes in Indo-Burmese arc, or Northeast India, what we call, or the largest earthquake which we had in 2004, which is the one Sumatra earthquake. So it's this small motion which causes strain accumulation in these plate margin regions, where Indian plate actually collides with Eurasian plate here and the Sunda plate here. So it's this interaction between these two plates. I mean, if I had lots of oil, then I could have poured that oil between these two boundaries just to avoid these earthquakes. But unfortunately, the interaction is not friction-free. So it's the friction which causes these two plates to get stuck together. They get locked, and when the strain, when the accumulating strain exceeds the strength of that rock, then the earthquake occurs. So that's what happens at these plate boundary regions. I'll give you an example here, which is Garhwal Kumaun region, and we chose this. I have chosen this region here because we feel that it is one of the most dangerous segment of the Himalaya where a big earthquake can occur anytime. So the story started, the story about strain accumulation and strain release started with an earthquake which occurred in 1906, which is known as San Francisco earthquake. And what people realized was that there was a fault here. Faults were known by the time. Plate tectonics was not invented. So there was a fault here, and after this earthquake, this fence which was running across this fault, which was continuous, it got offset by almost like 6 feet. So then then there was a gentleman called Reed. He suggested that, look, we know that earthquakes release strain. So that means now this offset implies that the energy was released during this earthquake. The same energy was accumulated before the earthquake. So that's such a simple theory, which is known as elastic rebound theory. So all our work, whatever we do using GPS, is based upon this, that before the occurrence of earthquake, strain accumulates, and then it gets released during the earthquake. So it becomes important to monitor this strain accumulation, to measure this strain accumulation, to know which are the regions, where are the places, what is the rate. So that's the whole thing we do in GPS measurements. So if I move further, well, it's not that such offsets were not seen earlier. We had our own example in 1819, which is this earthquake. There was an earthquake in Gujarat, in Kutch actually. This occurred in 1819, and it caused an offset on the ground. And that offset was called as Allaban, because people thought that this is a band, a dam created by the god. So that's why it's called Allaban. So we had these observations earlier. Incidentally, this is the first observation, first faulting observation in the world which was seen. Plate tectonics was not invented by the time. So if I go a little bit into detail, then that's what happened during an earthquake cycle. I said strain accumulates. So that period of strain accumulation is called as interseismic phase. That's when the energy gets accumulated for an earthquake, and then this is what we all of us are hunting for, nucleation phase. That probably this, if we one day if we can we know something about it, then probably we will be able to predict earthquakes. But that day has not come as yet. And then you have a phase which is called coseismic phase. That's when all this energy which accumulated over 100 years or over 1,000 years, it gets released. So that's called coseismic phase. And then we have a period of relaxation. That okay, now the Earth is relaxing. So that's called post-seismic phase. So we actually all of our observations are made here to know something about this coseismic phase. If I draw a cross section, if I draw a vertical cross section, then coseismic release occurs on the shallow part of the Earth. The interseismic strain accumulation, it is caused by the motion at the depth, which loads the fault on the shallow surface. So in the context of Himalaya, if I take a cross section, then this is where the this is the mountain front. So if you're traveling from Delhi to Dehradun, so the place like Mohand, when you first hit the mountain front, so that's where the mountains start, and it's almost like 100 kilometer or 120 kilometer, which is where the strain actually accumulates, which is where these great earthquakes actually occur. So this statement is true all along the Himalayan arc, which is almost like 2,800 kilometers long, and it is the lower part of the fault here which loads the upper part here. So the key here is to know that how this lower part is loading the upper part. If I show you on time scale, then so if you have a GPS, if you're measuring displacement, then in the interseismic period you are seeing that it is moving, probably at a rate of fraction of a millimeter in a month, and then the earthquake occurs. So that's when all the strain is released, and then you have some nonlinear period which is called as post-seismic phase, and then again the cycle builds up. Again the preparation for the next earthquake gears up. So that's how the earthquake cycle operate in convergent plate margin, including Himalaya. So with this background, I'll come to Himalaya, which is here, Garhwal Kumaun region. In this region, we believe that earthquake has a great earthquake has not occurred probably in last 700 years. So and we know that this region is the convergence rate is about 2 centimeters per year across this segment here. So we have enough strain which can be released during a big earthquake. That's the and we believe that this is probably the most dangerous segment, because elsewhere earthquake has occurred probably 200 years back or 300 years back, but it's only in this region where earthquake has not occurred in last 700 years. So that's the region we are targeting, this region, Garhwal Kumaun region. So if I take a cross section here, so that's the fault. That's the fault where we expect big earthquake to occur. So that's the fault on which the big earthquake they generally occur here, and that's where the strain is going to accumulate. So what we did was, well, we have some idea of strain accumulation, but let me skip this slide. So what we did was that we put almost like 30 GPS stations in this region. It took us 3 years to do this. So these are the 30 GPS stations which are ticking continuously in Garhwal Kumaun region, and the rate here is that. So I'm fixing this part. I'm assuming that this part is not moving, and then I'm showing these rates with respect to this part. So you see that gradually as I move northward, these arrows, the size of these arrows is increasing, so there is a gradational increase in the displacement rate. Now, the beautiful part here is that, now these are the beautiful sites. For those who are interested in pilgrimages, this is Yamunotri, this is Gangotri, this is Kedarnath, this is very close to Kedarnath. This is another site, Nanak Mata, which is a Sikh pilgrimage. So, it takes you to all these places and do some exciting work. So, so what you do is now is that you take you take a cross section, you take a profile here and plot them, and you see that there is a gradational change, gradational increase in the displacement rate, and that's instantaneously tells you that strain is accumulating in this region, and it tells you that the strain is accumulating at a slip rate of almost like 2 centimeters per year. Now, for a big earthquake to occur, you need almost like a 5 meter of slip. 2 centimeters per year, it will take only 250 years for slip of 5 meter to be accumulated. What we are saying here is that this region is accumulating strain for last 700 years. So probably this is the region where you can expect big earthquake. Now, what you can do is, rather than, these are simple results, but actually you can do a lot of inversion, and then you can actually see that which are the places which are strongly locked, where there's absolutely no leakage between the subducting Indian plate and the overriding Himalayan wedge. What is the extent of locking? So that's what you can do, and this is what has been done here. So this part is sort of, you have almost no slip here. I mean, the two plates are stuck perfectly with respect to each other. So there is absolutely no leakage here, the frontal part. And then as you move northward, the slip increases. So that means here there's absolutely no strain accumulation. It's only here in the frontal part where the strain is accumulating very strongly. You can convert this map into a more conventional map, which is known as locking map, and this is very scary. A lot of people think that there are several features on Indian plate which influence this locking, which influence this strain accumulation. So they sometimes say that, well, these features will not allow these big earthquakes to propagate over long distance or to cause big earthquakes in this region. But unfortunately, that's not true. So there is a feature called Delhi-Hardwar Ridge. There is a feature called Muradabad Fault. They don't show up here. So the locking is absolutely almost like homogeneous, and that's very scary. Thank you. That's very scary. So this shows that almost like 150 kilometer width area is perfectly locked. So we have a perfect scene here. That strain accumulation is very large, almost like 2 centimeters per year. The strain has not released in the last 500 to 700 years, and the locking is almost like homogeneous. So there's hardly any place to hide. Those regions, those you see, the more reddish region, they are absolutely perfectly locked, and those are regions which are going to be affected adversely during the next big earthquake. So that's what you can do using GPS measurements in such regions. I can give another example here, which is Indo-Burmese arc. I'll be very quick in this case. So the controversy here was that a lot of earthquakes occur here, and the culprit was considered that there is a fault which is called Sagaing Fault in Myanmar. So people used to think that it's that fault which accommodates the plate motion, the convergence between Indian plate and the Sunda plate on this side. But then we put our GPS network here. This is a tough terrain to work actually. We put our GPS network here, and we found that Sagaing Fault is here, and that's our boundary. We found that what people thought was actually not fully correct. The motion between Indian plate on this side and the Sunda plate on that side is actually being segmented, is actually being accommodated at Sagaing Fault which is here. So 36 millimeter per year of motion between India and Sunda plate is part of it goes into Sagaing fault, and part of it goes into in the Indo-Burmese arc, and we found a fault which is called Churachandpur-Mao fault, which accommodates this motion of 16 millimeter per year. Now this was kind of a discovery, because this fault, the fault was mapped, but nobody thought that this fault is basically a plate boundary fault. Now this has got several implications in terms of, because what we suggested was that probably this fault does not accumulate strain. It slips quietly. It does not accumulate strain. The friction is very low here. But that has been now sort of challenged, and people are saying that, look, what you're saying is probably right here, but then it is this part which is in Bangladesh which is accumulating strain. So that's such things keep happening. So with this, what I'll do is I have finished my talk. So what I want to emphasize is that these GPS measurements of crustal deformation, they're important. They have revolutionized the world in terms of time synchronization, in terms of Google Map, in terms of navigation. But in seismology, in earth sciences, it's absolutely revolutionary, and they helps us in understanding earthquake occurrence processes, assessing seismic hazard. We need to take more such observations, and it's all about all the research is all driven by good and large amount of data. With this, I'll end my talk, and I must thank all my peers, all my supervisors, and those who have helped me in reaching here. Thank you very much.